First detected on the 13th of January, C2026A1 MAPS was quickly identified as a likely member of the Kreutz family of sungrazing comets. Archival images later revealed that it had already been faintly recorded in December 2025, unnoticed until its orbit was calculated. Its projected perihelion, closest approach to the Sun, is expected on the 4th of April 2026. On that date, the comet will plunge extraordinarily close to the solar surface, passing only a few 100,000 kilometres above it. At such distances, survival is never guaranteed. A newly discovered comet passing this close to the Sun inevitably attracts attention. One widely circulated headline has already posed a tantalizing question. Could this comet briefly become visible in broad daylight as it makes its solar dive? If it survives its extremely close perihelion passage, some estimates suggest it could brighten dramatically in late March and early April. Many Kreutz Sungrazers do not survive. Some fragment, some flare spectacularly, and some disintegrate entirely in the final hours before perihelion. All of them enter one of the most extreme environments in the solar system. Astronomers are watching closely, and so are we, because Sungrazers are not merely icy relics responding passively to sunlight. They are stress tests. And stress reveals structure. As C2026A1 approaches perihelion, the question is not only how bright it will become, but what its behaviour will reveal about the forces at work near the Sun. When a small body plunges into an electrically active plasma environment, what should we expect to see? This is not an I-class interstellar visitor like Oumuamua or Borisov. It is classified instead as a long-period comet, which standard models assign to the hypothesized Oort cloud, a vast, distant reservoir of icy debris thought to surround our solar system. There is only one small complication. The Oort cloud has never been directly observed, not imaged, not sampled, not detected. Its existence is inferred from the patterns in the orbits of long-period comets, a theoretical construct proposed in 1950 to explain the apparently random directions from which they approach the Sun. In other words, this comet is said to originate from a region that remains observationally unconfirmed, a gravitational ghost at the edge of the solar system. In short, the comet is observable, its proposed birthplace is not. The conventional story begins with that assumption. Long-period comets originate in the hypothesized Oort cloud, invoked to explain their apparently random arrival directions. Within that framework, a comet is described as a frozen remnant from the outer solar system, a mixture of water ice, volatile compounds, and dust. As it approaches the Sun, solar heating increases, ice sublimates, gas escapes, dust is carried outward, and a coma and tail forms. If the comet ventures extremely close to the Sun, as members of the Kreutz sungrazing family do, intense heating may trigger rapid sublimation and structural failure. Fred Whipple's dirty snowball model provided a coherent framework for decades. Comets, we are told, are the Rosetta Stone of the solar system, pristine relics preserving the chemistry of its earliest epoch. It remains the default explanation, yet space-age observations have complicated that picture. The Sun does not radiate into a vacuum. It sits within plasma, ionized gas threaded with magnetic fields and permeated by electric currents. The solar wind is not a neutral breeze. It is a structured outflow of charged particles embedded in a dynamic magnetic environment. NASA states plainly, quote, "More than 99% of the visible universe is plasma." End quote. That simple admission reframes the discussion. If the visible universe is overwhelmingly plasma, then celestial bodies moving through it cannot be treated as isolated thermal systems. They are immersed in an electrically active medium. When C2026A1 approaches the Sun, it does not simply get warmer. It enters increasing plasma density, stronger magnetic field gradients, changing electric potentials, and the heliospheric current system. In plasma physics, bodies immersed in plasma acquire charge. Surface potentials develop and double layers form. These are thin regions of intense electric field separating plasmas of differing properties. Under the right conditions, those layers can collapse, and when they do so, energy is released. Nobel laureate Hannes Alfvén, one of the founders of modern plasma physics, cautioned astronomers against ignoring electromagnetic effects in space. In his 1970 Nobel lecture, he stated, quote, "In reality, space is not empty but filled with a plasma." End quote. That observation is not controversial, it is foundational. Alfvén emphasized that plasma behavior cannot be understood simply by extending neutral gas models into space. Plasma introduces collective effects, electric fields, currents, and instabilities that behave differently from gravitational systems alone. If plasma dominates the visible universe, electromagnetic processes cannot be dismissed when interpreting celestial events. C2026A1 is about to plunge into the most intense plasma environment in our solar system. It would be surprising if plasma effects played no role. This would not be the first time a sungrazer approached the Sun during heightened coronal activity. In December 2011, the Kreutz Comet C W3 Lovejoy passed extraordinarily close to the solar surface. During its perihelion passage, coronal mass ejections were observed in close temporal proximity. Mainstream solar physicists describe the alignment as coincidental, noting that CMEs are understood to arise from internal magnetic instabilities in the corona. Electrical engineer and plasma advocate Donald E. Scott has suggested a different possibility, that a small conductive body plunging through steep plasma gradients could disturb an already unstable coronal configuration, not supplying the energy for a CME, but potentially triggering its release by perturbing a double layer or local current system. In complex plasma environments, small disturbances can precipitate large-scale reconfigurations. C2026A1 belongs to the Kreutz family, fragments of a once larger progenitor comet that now follow plunging near-solar trajectories. Kreutz Sungrazers have a dramatic history. Some disintegrate completely, some flare unexpectedly, while others fragment dramatically near perihelion. Comet Ikeya-Seki became one of the brightest comets of the 20th century. As it approached the Sun, it fragmented into several pieces. The breakup was rapid and energetic. Thermal stress is the standard explanation. However, the event occurred under extreme plasma immersion, precisely where electric field gradients and current densities intensify. It remains a useful comparison. Many comets display sudden brightness increases, outbursts that do not scale smoothly with solar distance. These are usually attributed to volatile pockets exposed by cracking, rotational effects, and structural collapse. Yet, laboratory plasma experiments show that when potential differences shift rapidly, surfaces can emit localized jets, material can be ejected explosively, bright filamentary structures appear, and surface erosion can occur in arc-like patterns. Electrical discharge does not require high temperature alone, it requires potential difference. If C2026A1 exhibits abrupt, localized brightening near perihelion, plasma interaction should at least be considered alongside thermal explanations. In 1996, Comet Heliospheric surprised astronomers by emitting X-rays. As NASA's Marshall Space Flight Center noted, quote, "The discovery of X-rays from Comet Heliospheric was completely unexpected." End quote. Comets were not expected to shine in high-energy wavelengths. The accepted explanation involves charge exchange, highly ionized solar wind particles interacting with neutral gases in the coma. That explanation is reasonable on the face of it, but it confirms something important. Comets are electrically interacting bodies. They are not passive ice blocks evaporating in sunlight. They are immersed in a plasma flow, exchanging charged particles with the solar wind. If C2026A1 produces high-energy emissions near perihelion, it will not be anomalous. It will be plasma physics in action. The European Space Agency's Rosetta mission to 67P complicated the traditional snowball narrative. The comet's surface displayed steep cliffs, consolidated terrain, and sharply localized jetting regions. Following the Philae Landis touchdown, mission scientists remarked, quote, "The surface is much harder than expected." End quote. If comets are primarily loosely bound aggregates of ice and dust, why do some surfaces behave like consolidated rock? If sublimation alone drives jets, why do emissions often emerge from discrete, sharply defined regions? Electrical discharge models predict localized emission sites, areas where charge gradients concentrate. Rosetta did not overturn sublimation, it revealed complexity. C2026A1 offers another opportunity to observe comet structure under extreme stress. The Sun is not simply a glowing sphere of hot gas. It is a dynamic star embedded within a vast electrical environment. NASA's Solar Dynamics Observatory describes it this way, quote, "The Sun is a dynamic magnetic star, releasing charged particles in a stream known as the solar wind." End quote. We are talking charged particles, magnetic structure, and dynamic interaction. Extending outward from the Sun is the heliospheric current sheet, a vast wavy surface separating regions of opposite magnetic polarity. It undulates through the solar system. When a comet crosses regions of shifting magnetic polarity and electric potential, it does not simply experience uniform heating, it encounters electrical structure. In plasma systems, boundary crossings can trigger instability, reconfigure double layers, and produce energetic emission. If C2026A1 crosses current sheet boundaries near perihelion, we may observe corresponding changes in brightness or tail structure. That would not contradict established physics, it would illustrate it. Many comets deviate slightly from purely gravitational orbits. These deviations are typically attributed to asymmetric outgassing, jets acting like thrusters. That explanation is reasonable. But plasma immersion introduces additional forces. Electrical interactions can exchange momentum. If orbital deviations exceed what measured outgassing predicts, the discussion should remain open. The heliosphere is not electrically neutral. If C2026A1 brightens dramatically, headlines will follow. If it fragments spectacularly, speculation will follow. History shows that when celestial events surprise us, public imagination sometimes leaps toward exotic explanations before revisiting fundamental physics. Yet, the more interesting story may lie not in aliens, but in plasma interaction. The universe is electrically structured. The Sun is electrically dynamic. Comets are participants in that environment. Sungrazers offer something rare, a repeatable class of extreme events. Each perihelion passage is an experiment. If comet behavior is purely thermal, we expect smooth brightening correlated with solar distance, sublimation-driven jet scaling, and gradual structural degradation. If electrical processes are significant, we might observe sudden energetic outbursts, localized emission zones, rapid fragmentation under peak stress, strong magnetic alignment of ion tails, and motion anomalies not tightly correlated with outgassing. These are observational questions, not ideological ones. As perihelion approaches, telescopes and solar observatories will gather imagery and spectra. Brightness curves will be plotted, fragmentation events catalogued, and tail morphology analysed. Interpretations will follow. The question is not whether the comet will behave dramatically. The real question is whether plasma physics will be granted a place in the interpretive framework. C2026A1 is not just a relic of primordial debris. It is a body plunging into a plasma environment of extraordinary intensity. Whether we describe it in thermodynamic or electrodynamic terms will shape what we think we are seeing. Quote, "What we observe is not nature itself, but nature exposed to our method of questioning." End quote, Werner Heisenberg. That is not merely spectacle, it is a natural experiment, and natural experiments deserve open inquiry. We plan to revisit this comet after perihelion and compare prediction with observation.